Okay, so starting our next unit, we are going to look at logarithms and exponential functions. So we will start with taking the derivative of the natural log. So we have been using natural log, and we think of it in terms of the inverse function of an exponential of e to the, but it actually has a calculus definition. So the actual definition of the natural logarithmic function is an integral from 1 to x, integrating the function 1 over t dt for positive x's, because remember the natural log is not defined at 0 or for negative numbers. You can't take that. So when we look at this as a function, it is a function because if I say the natural log of 2, that just means I want the integral from 1 to 2. I replace the x with with the number, just like I would for any other function, 1 over t dt. And now this is a definite integral, which means this answer will be a number. So the natural log of 2 is a number, and when I do the integral, I would also get a number. So same thing if I did natural log of 7, now I'm talking the integral from 1 to 7 of 1 of t dt. So we can write a function in terms of an integral, and it is still a function. We're just calculating the value of the integral over that interval. So if we remember about natural logs, the domain is all positive real numbers. That's all positive real numbers. Its range is from negative infinity to positive infinity. And then the function is also continuous. It is increasing over the entire domain. It was 1 to 1, and it is concave down. All of those are true over its entire domain. So if I go back and remember what the graph of a natural log looks like, at 1, we have that the natural log of 1 is 0, because what do I need to raise e to get 1? I need to raise it to the 0 power. So, and then my function is going to look like this. Natural log of 1, if I use the definition, is from 1 to 1 of 1 over t dt. And when I take the integral over an interval of length 0, we get 0. So we see what we knew about the natural log function is true with this new definition of the natural log function. We still get natural log of 1 is 0. So let's look at some review from pre-calculus. Let's look at our properties of logs. And I'm going to remind you, a log is just an exponent. When we think of logs, we are thinking about exponents. And I didn't spell that right. There we go. A log is just an exponent. So what this says is when the exponent is 0, right? Or I can think of it, this says what is the exponent on, natural log is base e. What is the exponent on e that gets me a 1? The exponent is 0. So the log is just the exponent, okay? So when I had a product, remember if I am multiplying x squared times x cubed, when I'm multiplying with like bases, what do I do with the exponents? Well, my exponents get added. So since I am looking at the natural log as an exponent, if I was multiplying inside, that's with like bases, then the exponents, ln of a and ln of b, would be added. If I'm multiplying with like bases, I add the exponents. And then here I have a power 2, or I have a ln is talking about an exponent. And the n on the a is also an exponent. So when I raise a power to the power, I multiply my exponents. So I get 2 times 3, or I would get x to the 6th. So one of my exponents is ln of a, and the other exponent is n. So that when I have inside the natural log, when I have a power on what's inside, that can actually come out front to be multiplied, should multiplying the exponents. And then with division, hopefully remember, if we are dividing like bases, then we are subtracting the exponents, and a natural log is just an exponent. Also, in pre-calculus, we looked at this function, 1 plus 1 over n raised to the n, if I took the limit as n approaches infinity. So the language that we used in pre-calc was as n approaches infinity. We didn't actually get limit notation yet in pre-calc, but the idea is as n approaches infinity, this function is going to approach e. So that was our definition in pre-calculus, basically, of what is e. And we did some work with it, where if we just plugged in larger and larger and larger n values, we were approximating the e value. We looked at that on our calculator. Well, we now have a calculus definition. Since we had a calculus definition for the natural log function, since e is just a number, natural log of e, I plug in the number just like I did natural log of 1, natural log of 7, natural log of 2. E is just a number. So e is the number that gives me the length of that interval from 1 to e in my natural log function, where that area is exactly 1. That is the definition of the natural log of e. So now that we have this new natural log function defined with calculus, we should be able to take the derivative of it. So if I want to take the derivative of the natural log, let's use the definition that we have of a natural log. Our natural log is the integral from 1 to x of 1 over t dt. So I want to take the derivative of that integral. If I'm not mistaken, this is going to be the second fundamental theorem of calculus. Do I have a number at the bottom? I do. So then the second fundamental theorem of calculus says that the derivative, we just plug the function up above into the function we're integrating. So I get 1 over x is the derivative. If I had an x squared up there or a function, I would do chain rule. I can do chain rule here because the derivative of x is 1. So that means 1 over x times 1. But what this means is that the derivative of the natural log of x is 1 over x. So let's practice that. Here I have the derivative, or I have the function y equals the natural log of 4x. And what I see is that inside the natural log, I have another function, which means here I will need to use the chain rule. So if I want to find the derivative, y prime, the derivative of my outer function, the natural log, is 1 over whatever is inside my natural log. And then I'm going to use the chain rule. So I'm now going to multiply that by the derivative of 4x. So I'm going to get the derivative of 4x is 4, which conveniently reduces, and I get 1 over x. Well, that's interesting. The derivative of the natural log of 4x is the same as the derivative of the natural log of x. I wonder if that would always be true. So the derivative of the natural log of any number times x would be, y prime is going to be 1 over ax times, that's what's inside, and then I multiply by the derivative of ax, which is a, and sure enough, that constant reduces. So when I just have a constant multiple inside my natural log function, that's going to reduce out due to chain rule, and I'm still going to get 1 over x. So if you think you understand this after one example, go ahead and pause the video for a minute and try to take the derivative of the natural log of the quantity x cubed plus 1. So when I go to take the derivative here, the derivative of the natural log is going to be 1 over whatever was inside the natural log. So I'm going to have 1 over x cubed plus 1. And then because I have a function inside, this is a chain rule. So now I'm going to divide by the derivative of the inner function, which is derivative of x cubed is 3x squared. And if I am multiplying fractions, basically what that means is I get 3x squared over x cubed plus 1, which cannot be reduced. So that would be my derivative. What I should see with what's happening here is that if I'm going to take the derivative of the natural log of any function where u is a function in terms of x, what I see is in the denominator, whatever function was inside, and then my numerator is always going to be the derivative of the inner function. So I can just directly go to that format. So like if I said, find the derivative of the natural log of 3x squared minus 7, you could go straight to derivative of the natural log. 3x squared, I said. The derivative of the natural log puts 3x squared minus 7 in the denominator, and then the numerator is going to be the derivative of 3x squared. So the derivative of 3x squared is 6x. You don't have to take the extra step to show the 1 over times derivative of the inner function. 1 over the inner function times the derivative of the inner function. It is always going to be of that form. The derivative of the inner function goes on top. So that's if we're taking the natural log of a function. What if I have a chain rule problem where the inner function is my natural log? Okay, let's take the derivative. So I'm going to do the derivative of the outer function. Some of you like the dy dx notation. Both of those are the same. So the derivative of the outer function, derivative of cosine, is negative sine of ln of x. My inner function is still my inner function. And then I'm going to multiply by the derivative of natural log of x, which is 1 over x. So when I write this, negative sine of ln of x over x would be my derivative. So I'm still just following the chain rule, and I'm just using this new derivative that we've learned, the derivative of the natural log of x. This next example is a product rule. If you think that you can do this one, go ahead and pause the video and try it yourself. So for the derivative of a product, I want the derivative of the first times the second plus the derivative of the second. The derivative of ln of x is 1 over x times the first, which x was the first function. So if I simplify this, I'm going to get the natural log of x plus 1. Hopefully you did that right using a product rule. Oh, yuck. I have a function inside of a function. Ugh. So I have two chain rules here. So remember, this is the natural log of x cubed minus 2 to the 1/2. That square root is just a power. So if I'm going to do this derivative, f prime of x, I am going to do the first outer function, which is going to get me the 1 over the natural, 1 over x cubed minus 2 to the 1/2. And then I'm going to multiply by the derivative of the next inner function, which is the exponent. So what that's going to look like is I'm going to now have 1/2 times the x cubed minus 2, because my exponent comes out front, and then I subtract 1 from the exponent, so to the negative 1/2. And then I have my innermost function, so that's going to be 3x squared. So my first outer function, my second, and then the third, which is yucky. And then when I start simplifying that, I'm going to have, let's see, in my numerator, I have a 3x squared. In my denominator, I have a 2 times x cubed minus 2 to the 1/2. And then this x cubed minus 2 to the negative 1/2 should be in the denominator. Well, when I multiply with like bases, I just add my exponents. So here I have x minus 3, or x cubed minus 2 to the 1/2 times itself, which means I'm squaring that. So if I simplify this, I end up with 3x squared over 2 times x cubed minus 2. Now, um, I don't like lots of chain rules, and we have properties of logs. And I know that if I have an exponent inside my natural log, I can bring that out front and make it a product. So I'm going to attempt this problem in a different way. Instead of saying f of x is the ln of the quantity x cubed minus 2 to the 1/2, I'm going to bring that 1/2 exponent out front times the natural log of, actually, I don't need the parenthesis there, times the natural log of x cubed minus 2. And now I don't even need a product rule. I just need, this is a constant multiple. So the derivative is going to be 1/2 times the derivative of the natural log is 1 over x cubed minus 2. And then the derivative of the inner function goes on top. Isn't this the same thing we got when we did all of that simplifying? So you can use properties of logarithms to make the derivatives easier. That's a really nice thing about using taking the derivatives of logs. So if we look at this one, who wants to do a quotient rule and a product rule and two chain rules in the process of taking this derivative all inside the natural log? So instead of doing that awful derivative, what I'm going to do is I'm going to rewrite the natural log or using properties of logs. So the first thing that I can do is I have a numerator and a denominator. So I'm going to break that up into the natural log of x times x squared plus 1 quantity squared minus the natural log of, and I'm going to write this with an exponent, 2x cubed minus 1 to the 1/2. So now that gets me a little easier, but I still have several properties I could use. So now I'm going to use the exponent property. Oh, no, sorry. I'm going to use the product one here. So this, I'm going to separate my product and go natural log of x plus the natural log of x squared plus 1 quantity squared minus, I still have the natural log of 2x cubed minus 1 to the 1/2. Now I'm going to use the exponent. So that's a product. I'm going to use the exponent property here. So I'm going to rewrite this now as the natural log of x plus 2 times the natural log of x squared plus 1 minus 1/2 the natural log of 2x cubed minus 1. Now, it took a little bit to use those properties of logs to get to this point, but now, since g of x is just the sum of natural log functions, g prime of x becomes relatively easy. Derivative of natural log of x is 1 over x. The derivative of the natural log, 2 times the natural log of x squared plus 1. Derivative of the natural log is x squared plus 1. Derivative of the inner function, 2x, goes on top. And then I have minus 1/2 times derivative here. I get 2x cubed minus 1 in the denominator because the derivative of the natural log puts what's inside in the denominator. And then the derivative of my inner function is that. And now this becomes very easy to simplify. 1 over x plus 4x over x squared plus 1 minus 3x over 2x squared minus 1, because 2 divides into 6 3 times. Way simpler. I did not have to use a quotient rule. I did not have to use a product rule. I didn't have to use a power rule. I can just do straight logarithmic derivatives and makes that process much easier. Now, it would be really nice if I could use this method even if I don't have a logarithm. So here I want to find the derivative. Right now, I have to use a quotient rule. I have to use a power rule with a chain rule twice, once in the numerator and once in the denominator. Yuck. But we have this process called logarithmic differentiation, which is going to allow us to use log properties to simplify the derivative. So if y equals this function, x minus 2 quantity squared over the square root of x squared plus 1, I can do the same operation or the same function on both sides of this equation, and the values would still be equal. So what I'm going to do is I'm going to take the natural log of both sides of my equation, which is going to allow me to use log properties. So if you are able to do all of those logarithmic properties in your head, what I see is I have the quotient. So the numerator, x minus 2 quantity squared, but the exponent is going to go out front, minus the denominator is the natural log of x squared plus 1 to the 1/2. So the 1/2 goes out front. If you're able to do all of those steps at one time, go ahead. But now I have to use implicit differentiation because I now have a function of y. So when I take the derivative of the left-hand side, the derivative of the outer function, natural log of y is 1 over y. And then when I multiply by the derivative of the inner function, I get y prime. So I have to use chain rule on the left. And so now when I take the derivative on the right, I have 2 times derivative of the natural log of x minus 2 is 1 over x minus 2, and the derivative of the inner function is 1, so I'm good, minus 1/2. The derivative of the natural log is 1 over x squared plus 1 times the derivative of the inner function. Those are going to reduce. So what I now have is that y prime over y equals 2 over x minus 2 minus x over x squared plus 1. So now I don't want to know what y prime over y equals. I want to actually know what the derivative of y is. What is y prime? So y prime is going to be, I multiply both sides by y, so it'll be y times what I got when I did logarithmic differentiation. And now I don't want it in terms of y, but do I know what y equaled? Yes. So now my last step, I find that y prime is going to equal y was x minus 2 quantity squared over the square root of x squared plus 1 times 2 over x minus 2 minus x over x squared plus 1. So that process, logarithmic differentiation, allows me to use log properties to simplify a really ugly function that would otherwise take a lot of formulas or a lot of derivative rules to take the derivative of. So